where our true data is, had the curve, if the true mu is outside of the original alpha risk, which is rejected from the hypothesis, in which case the second curve doesn't matter. It's the first curve that determines whether we reject the hypothesis. The second curve tells us how much beta risk we're taking as we do that. And as the deviation between the two mu's starts to grow, we start to get a decreasing beta risk, because less of the true curve is on the free side of our alpha. So our beta risk in this case might be much smaller because we're seeing more and more of the curve falling outside. So perhaps our beta risk at this point right now is 2.9, and our power has risen to 2.1. It's a slightly more powerful test that is in fact capable or more likely to identify that mu0 is in fact off. If I continue this process for other samples of data that might be even farther from my original, this may be a second mu that's even farther over, at this point, the amount of data that would cause me to reject the null hypothesis, the alpha risk, if you will, which is getting larger each time, is in fact growing. So the beta risk that I'm taking with my data has been shrinking over time. So my beta at this point might be 0.6 for a power of 0.4. So my test is getting more and more powerful as I go. So if I take perhaps one last curve that I can fit here on the screen and go with a mu sub 3, the alpha risk for that is way on the far side. So if in fact I was that wrong to begin with, the test is very, very capable of finding that, because my beta risk in this case might be 0.2 and my power of 0.8 as I go through. So what I'm looking for is the more wrong I was up front, the more likely the hypothesis testing that I'm doing will spot the problem. But if I'm only a little bit wrong, if the true mean is very, very close to that original mu, this test is very, very unlikely to find it at a 0.01 alpha. So if I think in terms of where is the real beta risk associated with what's going on here, and compare that to the size of the deviation that I'm seeing between these data points, my typical beta risk will start out at 1 minus alpha. When I've got almost no deviation, I'm at my largest beta risk. Up here just under, that's the 0.99 I might have on an alpha 0.01. But it doesn't fall linear. I'm going to say a pretty dramatic fall. As I end up with larger and larger deviations, we'll have smaller and smaller beta risk. So if I kind of fill in the curve here and start off with a very large, small deviation, it's going to correspond to a very large beta risk. If I start out with a very large deviation, it's going to correspond to a very small beta risk as I go through. So I want to be careful. The more my data is off, the more powerful my test, but I can't guarantee it will be off. So I don't always want to go with an alpha of 0.01. Alpha of 0.01 appears to be minimizing risk, but it's actually potentially maximizing my beta risk if in fact the means are very, very close. So typically what I want to do when I'm working with my data is I don't necessarily want to go with that 0.01. To the extent I can on this screen, let's try a different alpha line through all my curves. Maybe take my beta up to 0.05, another classic number that we see. Why is 0.05 kind of the default number we use in statistics? And this is going to be the reason why. Because at 0.05, that area under the alpha curve gets larger and larger for each of these distributions. So this 0.9 might now be 0.55 and a power of 0.45. This 0.6 is way down now to maybe 0.35 for a power of 0.65. This 0.2 is way down now to almost 0.5 for a power of 0.95. So as I allow my alpha risk to grow just a little bit, I take a chance that I won't necessarily be able to detect my hypothesis being off. I reduce the beta risk associated with my process very, very powerfully. So at 0.01, I'm going to tend to be very, very high beta risk over here in this part of the curve. At 0.05, I'm going to be down here in a far less risky part of the curve. I could go to 0.1 on my alpha and really get out here on the curve. So those engineering applications where the thing we're most concerned about is the beta risk, there are strategies for dealing with that simply by taking alpha up. The way we say it is accept the largest alpha you can within your application, and that will minimize your beta risk. If you try to squeeze out alpha risk, you're only increasing your beta risk, which in some applications might be exactly what you want. So you've got to think like an engineer and decide which risk am I really trying to manage. But you want to be prepared using these tools to manage either side.